this lecture, I know it's a little bit to say it that way. But what we talked about was just this universal hashing where we're looking into having local interpolation. And we saw how we could hash actually keys from some pretty large domains, like variable length strings. And one of the nice thing was when you used all the different tricks of the trade, including the cross product and stuff like that, we actually only did one W-bit multiplication per W-bit per W-input bits. Okay? So we only got W half bits out. So again, think of W as 64 bits, then we get a 32-bit hash value. And I don't remember if I really said that, but of course you can get a larger hash value because all you have to do is to import one estimates similarity, it's using machine learning and stuff like that. But the point is just nobody knows how to implement a hash function that satisfies this nice quality. But we can satisfy it roughly, so it's called epsilon min-wise when we have it satisfied with a plus minus epsilon. And I also just want to say that this is used everywhere. Just the chaining and linear probing, even though this seems so simple and so naive, you will find it everywhere in industry. For good reasons, they're very efficient. Especially the linear probing, as Rasmus said, with the race car example, because of the sequential access. Basically, the main cost is just to go into a table somewhere, but the sequential access for the element to run is not too long, costs almost nothing. So you get to do searches in memory for a key almost as efficient as just doing a single random access within 20%. Okay. So how have people dealt with not having true randomness? There's this concept, as Rasmus mentioned, just that we have a k-dependent variable is one k-dependent hash function because it's truly random on any k keys. Okay, the classic example of these polynomials. And we have many solutions, and they're more or less fast, but it tends to get quite slow when we look at the dependence bigger than 5. And so the basic thing is, now when we have this k-dependent framework, then we can ask, now we have a clear measure for how good is a hash function, that's how independent it is. And then we can ask how much independence do we need for different applications. For chaining, you just want the expected search time to be constant, then you just need 2 independence because you just need the low collision probability. We've talked about that several times. But if you want things like saying that the maximum bucket size is log n divided by log n, then you need this kind of independence. And as Eva remarked last time, it doesn't mean that that can't exist hash functions with lower independence that don't work. What I'm just saying is that all you assume about a hash function is its independence. Then you need this level of independence for it to work. And this is also the nice thing about this framework, because if you prove that a certain amount of independence suffices, then you can just go down to the shop and say, what's the best hash function we have today with this level of independence? And if somebody finds a new, faster hash function with that independence, you can just plug it in instead. So then there's this cool hashing. We know it works with your logarithmic independence, and we know that you need at least 6 independence, linear probing 5 independence, F2 estimation 4 independence, and for minwise independence that we're going to talk about, the basic point is that to get this bias of epsilon, you need simple tabulation is, well, there might be other implementations, but on the computers I checked, it was the fastest 3 independent hashing scheme. It has a speed which is like 2 multiplication. That's again because these tables were very fast cache. Actually, on more modern computers, it seems like 16-bit characters work better. Then you have only half as many lookups, and the caches are getting really big. So there would only be 2 lookups for these 32-bit keys. And one of the things we see is it's not 4 independent, and that's very easy to see. You just look at the combinatorial combinations of 2 characters in each position, and you look at the hash values of these, and we just XOR them. And because you end up looking each hash value exactly twice, and because XOR, when you add things to itself, it just cancels out as a 0, then we end up seeing that the XOR of all the hash values is 0. So that means that if you know 3 of these hash values, you get the 4th one for free. So this thing with independence, in some sense, is a wrong question, because the result I had with Mihai is that even though simple tabulation is not more than 3 independent, it can solve all these problems in one shot. And it's extremely fast. As I say, I think it's about 3 times as fast as the best 3 independent schemes if you're, say, looking at 64-bit integers on the computer side. So, I mean, the scheme is well known. It goes, it's used everywhere in operations research and stuff like that. And Plus recommends it because it's 3 independent. And I guess there were experiments supporting it. Okay. But to prove that this works, you have to show that all this dependence you have in simple tabulation, we saw we got it as soon as we just looked at 4 keys, is not harmful for what we're doing. So it's there, it's everywhere, but we want to prove that it's not going to kill your application.
But if you replace the exclusive OR by addition,
then it also works. The exclusive OR has some nice advantages. For example, it means when you look at the hash values, the different bits are completely independent of each other. So it does give some advantages. But actually, originally we got our analysis to work only with addition and not with XOR. But XOR somehow is the fastest, certainly the thing the computers like the best, and it has a bunch of other advantages. But it works almost, you'd have to go through all the proofs, but as far as I recall, there's nothing that doesn't work with addition over some, say, prime field or something like that.
But with addition, is it 4 independent? Or
no. Well, I'm actually not sure. Well, I don't think it's 4 independent, but it may not be as bad as this case here. But again, we got this example very simple.
It is not 4 independent. Because in the example, if you add the numbers, they will always be even, so you have to...
That's exactly right. Excellent points. We have very good students here. So, anyhow, so what I'm going to talk about, this again looks nasty first. You see that you haven't seen it before. It's these Chernoff bounds that are going to hold. And the basic point is just we're looking at int balls that we're hashing into some number of bins that is not too small here. And then we have some query ball that we think is special because that's the one we're throwing in, and what we're worried about is how many other balls do we collide with. Okay, if things were totally random, then this query ball would just be thrown randomly and it would just be a random bin. But because we're dealing with hash functions which have dependence, the position of the query ball could depend on the position of the other balls. So it actually matters to see how many balls end up in the same bin as the query bin. And then we can say, how many things do we expect ending up in the query bin? Well, that's just the number of elements divided by the number of bins. So that's mu. And then we can ask, what's the probability that the number of things that end up together with the query bin deviates a lot from its mean? And here we have these standard Chernoff bounds. It's almost standard Chernoff bound. The only exception is that the omega should not be there if it was a standard Chernoff bound, and this thing should not be there. But otherwise, it's just the same bounds as if we have true randomness. This omega term basically just means that we have a delay. So it's like the Chernoff bounds say that the probability that we deviate a lot from the mean falls exponentially. And the omega just means that our rate of falling is somewhat slower. We get a little bit delayed because it's not by the exponent mu, but just some small constant times mu. And I should be honest that the constant depends on the number of characters. And then we have this additive term, which is the number of bins minus gamma, where gamma can be as big as you want. But it also affects omega. But you can basically think of this as being a kind of high probability. So with high probability, we get some delayed Janov bounds. That's one way of reading this kind of thing. Okay. And basically when you get Janov bounds, that's one of the most important tools we have in randomized algorithms to prove that things work. So if you get Janov bounds, a lot of things start working. So I'm not going to tell you how to prove the Janov bounds. It's complicated, but let me just try to illustrate for you why tabulation hashing, simple tabulation, gives you something that's fundamentally different from anything you can do with independence. So we're just going to see what happens when you throw n keys into 1 plus omega 1 bins. So we just have polynomially more bins than we have balls. And I want to claim that the number of keys ending up in the same bin is only constant. So nothing like that would hold with any constant level of independence. Here comes some obvious stuff, I get it. So the important part here is just that if we consider some set T of keys, then there will always be a subset of these keys that hash completely independent. And it's a logarithmic number of keys. Sorry, I shouldn't point to my fingers, it doesn't help. So that's really a very crucial thing, right? So we have independence everywhere. So normally in proofs of like the previous proofs we've seen, we have been able to argue, oh, we never consider events involving more than k things. We don't go that way here. Instead, we just say we look at a bunch of things, and then we claim inside that something is independent. And why is that? So we just say, take some character position where the keys in this set T we're looking at differ. And then A be the least common character in that position. So now we pick any key which has this A in position I. And then we reduce T to T prime by removing all the keys from T that has A in that position. And now we know that the hash of this key X, which has A in position I, is independent of the hash of everything else. Because the hash of X is now the only one that depends on the random value associated with position I for the character A. And now what we return is just recursively the key X together with the rest of the set reduced the same way. So we just recurse. And the basic point here is just that because we picked out the least common position, when we get from T to T prime, from T to U, we reduce the set by less than a factor 2, or at most a factor 2. And then the rest is kind of trivial. We just say, well, there can't be, now we know we have a set of U keys that hash independently. There can't be that many sets of that size. And so this is just counting the number of sets. We have n keys. We look at U of them, and U is not too big. And then we say, what's the probability that they all hash the same place? Now they're totally dependent. So that's just the number of bins to the U minus 1. And then we just do a union bound. Okay. So the important point here is just that simple tabulation is only 3 independent. And you can't make any claims that when you look at a small set of keys, unless it's at most 3 keys, that they all hash independently. But the point is that inside any set of super constant size, there's a subset which is also super constant size where all the keys hash totally dependently. And then we can use our usual kind of analysis. And this just illustrates why simple tabulation is so powerful. That yes, from the independence perspective, it's not doing well, but there's tons of independence in it. And in fact, inside every super constant set, we can find a super constant set which hash independently. So that's basically, what can you say, the inner thing in what's going on when we have to prove that we get Janov bounds and stuff like that. But then it also works for things like cuckoo hashing, but not quite as well as when you have total randomness, because the probability that something goes wrong is cube root n, 1 divided by cube root n. So if you did a true randomness, then it was 1 over n, but still from the perspective of making a sort of static cuckoo hashing table, this is perfectly good, right? So normally when you try, it's going to work well. It's only quite rare that you have to change it. And so for chaining and linear probing, it was pretty easy to argue things because we don't care about what happens with just a constant number of keys. But with cuckoo hashing, you really have to be very careful because all we have to worry about these small constant size abstractions. So it ends up being a delicate proof. But anyhow, so the basic point is here that we get both linear probing, we get chaining, we get Coco hashing, all using the same scheme. And I should also say that because we have these, this takes a while, sorry. Because we have these channel bounds, we also get that the highest loaded bin when we use chaining is log n divided by log n. All these different things come out. And so I claimed it was quick, and again I ran, it's a while back, I ran these experiments, but it was just on a 32-bit computer and a 64-bit computer. And we have these really fast universal schemes based on multiplication and shift, and they're unbeatable in speeds. And again, you should only look at the same computer. So that's very fast. The two independent one, that was the one we talked about, was showing 2 W bits instead of just W bits. So it's certainly going to be slower. Well, it's slower on this one here by a factor 3 to 4, which makes a lot of sense because internally it's only doing 32-bit multiplication, so it has to be 4 of them. But here we see how simple tabulation is doing pretty well. If we wanted to do this 5-independent scheme, then I ended up using almost 100 nanoseconds, so basically 20 times as slow. Okay. So then it all depends on the computer. The kind of funny thing is, on this 64-bit computer, it doesn't make a difference if you use 32-bit keys or 64-bit multiplication because it's just using 64-bit multiplication anyway in the registers. So there's some differences. But the basic point is just that simple tabulation works really, really fast. Okay. But what is far more interesting is to see what happens with something like linear probing. I mean, what happens with the theory. Mittelmacher has a very nice result which says that if you put up enough entropy, you just need something like 2 independent hashing for things to work. But there are plenty of cases in the real world where things don't have a lot of entropy. And we actually just took starting point something as simple as the keys being the numbers from 1 through n. And in fact, that is a very real problem because that's what's used in denial of service attacks. They just look at consecutive IP addresses. So again, when we live in a world with a lot of computer-generated instances, they all have very small entropy, and then any theory based on high entropy falls apart. But on the other hand, sometimes it does work. But so what we looked at was just what happened when we insert things with linear probing. Oops, I don't know what happened here. What happened when we inserted linear probing, and I ran 100 experiments where each time I used a different random seed, but it's exactly the same input. And the slowest one goes on top. And if you look at things like universal multiplication shift, what you see is that most of the times it performs extremely well, but sometimes it goes really bad. Okay, and the same with the 2 independent thing. It's also really fast some of the time, but sometimes really slow. And what's really happening here is that linear probing, if you just use 2 independent hash function, in expectation takes logarithmic time and not constant as it should. But it's far worse than that. Its behavior is something like 1 over x. It's the kind of behavior where most of the time it performs systematically good or systematically bad. So most of the time it performs systematically good, there's no collisions whatsoever, and it performs much better than random. But then when it gets systematically bad, it gets horrible. So this one is going towards infinity. Okay? And this is really nasty because this is when the system breaks down completely. It's when all these, all the placements of different things in the hash tables end up with this quadratic performance. Okay. And so those schemes I have here, all the horizontal lines are the schemes that are supposed to work well in theory. And as you can see, they really have very reliable performance. Even though these 100 experiments, there's hardly a deviation. So here I have simple tabulation. And here I have, well, it's another version of 5-independent hash function. And here's the thing implemented with Mersenne primes, which is significantly slow. But it's just nice to see how the theory pans out. But here, of course, I used a low entropy input structured input, but it's the same as when you do sorting. You do something like quick sort. Even though you would say you don't expect to have any problems because the probability that you get a sorted list is 0, it happens all the time in real life. And the same thing here. It's also the funny thing that what really kills many of these hash tables is when you try to hash something that's already hashed in the sense it's a small domain.
So what are the experiments? They're not just random.
No, so the input is just the numbers from 1 to n in a large universe. And then I retoss the random, so each experiment I pick random seeds, right? So each hash function is defined by some random seed. So and then you run a new experiment. And then you record the running time, and then I just sort them so that the things at the top are those that are slowest. Okay. So it's again, it's the same input, it's the same instance, it's just different random runs. Okay, so I think this is a very strong pitch for theory in the case of linear probing, right? Because multiplicative hashing like this multiplication shift thing and also multiplicative hashing with primes, Rasmus had already earlier showed that that was vulnerable. It's very unreliable under this typical denial of service attack where you just do consecutive numbers. I mean, people have talked about doing intelligent attacks, but this is in some sense the most unintelligent attack you can come up with, and yet it really works. And it's really nasty because 95% of the time it works really good, and then sometimes really, really bad. And so the point is that these kind of problems are very hard to detect for practitioners because it's hard to know for them if they are just unlucky, right? They knew that they were given a randomized outcome, so sometimes they could risk having big trouble. But how can they know if it's a systematic problem or not? Okay, and especially it's also bad because if they want to say, oh, it's a problem in the algorithm, and they run it again, then it works perfectly because it's just 1 in 20 times it's going to perform badly, right? So normally when you go back to your system and saying, does this part work, does this part work, when you go and test your hash function, it works great every time. You just say, I don't know what happened, right? So this is really where theoreticians need to come in and help. And indeed, linear probing have gotten this reputation of being fastest in practice, but unreliable, and then there are all kinds of ways that people have been dealing with that. At AT&T, they had some alternative table formats that would switch to, but that means you have duplication of code, you have many more things to maintain, so it's really bad in practice to have to switch to another system. And the upshot of this talk is that linear probing is in fact safe with at least the expected constant time per query for any input, but if you just use simple tabulation. And this is really the nice comfortable thing. There's so many scandals where people use bad hash table, hash functions, bad pseudo-random number generators. They get into big trouble. They do it when they try to generate codes for crypto where you pick some bad primes that are easy to guess and stuff like that. And every time the hackers would just say, oh, it's because you had a bad hash function. I know one that's much better. And then you try that one, and then one day it goes wrong, and then people laugh and say, oh, we knew that, but here's one that's much better, right? It's just this, and you never know when you can feel safe. But here you can feel safe. It's provably safe. You know what is the probability that things will go wrong. So simple hash function is, as I say, it's a powerful thing. It works for chaining, Coco hashing, and minwise hashing. Well, some exceptions, so it's for almost all you need. Okay, and the almost is why I'm going to continue this talk. So I'm going to talk about something that we call twisted tabulation. So one of the nice things that make chaining and linear probing work really well in many applications is not only that it works good in expectation for a single operation, but also, well, no, what makes it work kind of bad, sorry, is that if you look at square root n operations, then some of them are expected to take roughly logarithmic time, right? Several other speakers have talked about that the maximum bucket size is log n divided by log n if you use chaining. And with linear probing, the maximum run length is an expectation log n. So that means that if you have a kind of real-time system where you want to answer every query in constant time, then you're out of luck. You could might as well use a binary search tree. But if you have true random hashing, then what you can say happens with high probability is that any log n operations are dealt with in order log n time. Okay, so we can't give any promise for the individual operation, but as long as you're just looking at the amortized number or a logarithmic number of operations, then you're down to constant time, and you can promise that. And why is this useful? Well, I was doing this for AT&T, which was, we're dealing with internet traffic, and what happens is that all internet routers have buffers, in fact up to a megabyte, so log n is easily contained in a megabyte in most practical cases. And then we can actually promise we get down to constant time operation. does handle every window in logarithmic time with high probability. And it turns out that this little twist has a lot of nice effects, cleaning up a lot of things associated with simple tabulation, and it's really fast. Again, this thing is just the fastest kind of operations we have on a computer, so it's only going to take a fraction of a nanosecond. And just to sort of show the code, if you didn't like the other presentation here, so basically this is the code you would have for simple tabulation, but you just have an extra character that you pull out and then you insert, just to sort of show you that the code for these things are really simple. It's something you can program quite easily. So one of the nice things we get with twisted tabulations are some peanuts channel bounds. I already claimed channel bounds, but I will now claim we get them much better. So we have these 0, 1 variables where we want each variable xi to be 1 with some probability pi. And what we have it where true randomness is this exponential concentration around the mean. And so one of the basic things we use this exponential concentration for is that whenever we have a polynomial number of a logarithmic number of estimates, then they're all going to come out right with high probability. And that's how we use it in randomized algorithms. That's why we often have a log factor in these randomized algorithms. So if you want to implement this kind of thing with hashing, what you do is just that you use a hash value which is uniform in 0, 1, maybe with some precision. And then you say that you sample the guy xi if the hash value is less than pi. Okay? So if we only have bounded independence, the issue here is we only get polynomial concentration. So again, if we had full randomness, we get exponential concentration, but with k independence, we can't guarantee anything but polynomial concentration. But with twisted tabulation, we get the same formulas before. There's this little difference in here. It says the universe up to any constant size. And so the difference was with simple tabulation, what we essentially would get would be that u would be replaced by the number of bins. But the number of bins, if you're just tossing a coin, it's just, there are only 2 choices. Then you would have some constant in some constant, and then this term would completely dominate everything. So what we end up with is having that this error bound, or the high probability bound, is in terms of the universe size and not just the number of bins. And there's a similar situation with minwise hashing that's worked a bit with some deltables here, one of my students, which is that with simple tabulation, the bias we get is actually a unit is small, but it's small in the sense of that if the set is large, the bias is small. But here we then get that the bias is small compared to the universe size and not the set size. So again, we can trust that we get minwise hashing with small bias even when we're dealing with small sets. And again, we try to implement these different schemes. And I think the basic point to take home from here is just that twisted tabulation is only marginally slower than simple tabulation. And I think one of the other interesting things is you can use twisted tabulation as a very fast pseudo-random number generator. So what happens is when you want to use, so any hashing scheme can be used as a pseudo-random number generator because you just hash 1, then you hash 2, you hash 3, you hash 4, and so forth. And the point is, it's only the least significant bits that change. So instead of having to look up all the different characters, you only have to look up the least significant character each time, and that's why it's blistering fast. So comparing that with random from the C library, it's almost 6 times as fast. So what's the difference here is now you get a pseudo-random number generator that is 6 times faster, and it actually has the right distributional guarantees that allow you to do statistics and stuff like that. I mean, it should also be good for integration, basically any kind of connection where you use pseudo-random numbers. Rasmus and Tobias have some nice results in pseudo-random generation, but certainly this thing here is also going to be quite powerful. So I'm dividing the lecture in 2, sort of naturally. So just open problems in connection with simple and twisted tabulation. The obvious one is just to take any application where people have so far used truly random hash function and prove that simple and twisted tabulation works. And then a question I find very tantalizing is just, could this be the first implementation of quicksort? And that's something that has always bothered me, is this thing that we teach quicksort as one of the first things in the course of randomized algorithms. and it says in each step you need to pick the next pivot. You just generate a pseudo-random number, so you have some array you want to pick a random pivot from, and you just use a pseudo-random number to say which one should be the pivot. Gives you the index of the next pivot. And the issue here is just that there's all kinds of crazy dependencies, so we actually don't know how to implement such a pseudo-random number generator that makes that work. And it's a problem for many, many randomized algorithms. We have this concept of, in the same way as statisticians say you throw the next point, we say throw the next random number. And the point is just there's all these correlations between the decisions you made in the past, how in the quicksort thing, how the search tree developed and stuff like that. And we don't understand that. We don't understand if it's possible to generate random numbers that make these kind of algorithms work. I'm talking about convex or all kinds of things. The twisted seem to have some food. And yeah, then very recently, and I hope it still works, it seems to work most of the time, me and my students, Søren Dalgaard, Messing, Matthias, and Eva, we have been working to prove that this simple tabulation also works for power up to choice, right? So this is this thing that both Mike and Rasmus have been talking about. Normally to prove that it works, you need something like log n independence. The other scheme proposed, but the nice thing about simple tabulation is it's extremely fast. As I say, it beats 2 multiplications, so it's really moving very fast. So it just means that you could imagine using this power of choice even in high-speed situations like routers and stuff like that. So this concludes the first part of the talk, and I'm going to be continuing lecturing this way. There won't be really exercises here. This is more informing you about some hash functions that you can consider using for high-power situations. But I can't give you an exercise to prove something because it's actually nasty randomized. So in 5 minutes I'll continue, but if somebody needs to pee or gets a call or whatever, it's time now. So call it to get back. So more on tabulation. I claim I can do everything. So we argued earlier there was only 3 independent, but if you really want high independence, then you just have to do simple tabulation twice. Okay, so it's very simple. It gives you a lot of mileage just doing it once, but if you really want to go back to the old-fashioned paradigm of high independence, then all you have to do is just do it twice. So again, sort of motivating this whole thing here. So again, we had this really nice framework of k independence, where we had this polynomial, and this thing is ideal when it comes to the amount of space and randomness, because to get k independence, we use exactly k elements from the random fields. We couldn't hope to do any better than that. But in the evaluation of the hash value, it takes order k time. Okay, and somehow we would like to do better. Tabulation is sort of the most classic use of computers. I think it goes back to the French Revolution, which was the first time people realized the importance of tabulation when they got a lot of mathematicians to fill out logarithm tables and other things for the French Revolution. So, I mean, that's really the way to go if you don't want to recompute things all the time. But can we do anything about this? So, Siegel had a wonderful paper. I think it's so hard, but it's very interesting. So it says that he asked, can we get k-independent hashing using t less than k time? Right? So we know we can do it in k time. We just have to take each of these coefficients and multiply it and stuff like that. But can we do something with just k minus constant, this is huge independence, the size of the universe in some polynomial universe. He uses C as a constant time, and he uses this much space. And to formulate more or less what I said here, we think of both T and C as constant. He gets omega 1 independence, namely this much, in order 1 time using this much space. So at least, so that's all the best we could hope for. Oh, that was a negative thing, and then this corresponding positive thing. Sorry, what I said made nonsense. So he gets this high independence in constant time using this much space where he can pick epsilon however he wants. So epsilon is just 1 divided by C. Okay. And then you also write that it's far too slow for any practical application. So with double tabulation, that we get the same independence as he has here, but we only use this optimal C time, right? This is this time bound we talk about here, using this much space. And we can, in fact, also get what is really the optimal independence. That's a little harder to prove, but it's true. And using this much time, and again with the same amount of space. So that's what we're going to get with double tabulation. And as I said, it was far too slow for any practical application. Our schemes are very simple, but the analysis is not. It's harder than what's simple. Okay. So again, what we had was this simple tabulation thing. Here we saw that flip point dependence did not work. We now claim that simple tabulation is expected to yield some very fast, unbalanced, constant degree expanders. So expanders is some important area of relevant to randomized algorithms and stuff like that. And we actually get, in some sense, the best unbalanced expanders known. And that also applies, and when we apply it twice, we get this highly independent hashes. So how can I even talk, where do I see this unbalanced expander? So it doesn't have to be simple tabulation, we just think of any function that maps the keys into D characters. Okay, we can think of any hash function as hash value. Normally with simple tabulation we talk of the key as being divided into characters, but we can also talk about the output hash values as being divided into, say, 8 characters. So how do we define the unbalanced bipartite graph? We say that the right-hand side consists of these position characters, which is both the character and the position in the hash value. Okay, so if we have some function, so this is this function here, it gives me D characters, then the neighborhood of the key X is just each of these output characters together with its position. Okay, so kind of try to illustrate that. We have on the left-hand side, we have the universe of all keys, and each key has D neighbors, and it consists of a character and a position. So in some sense, we're dividing the right-hand side into D different parts that we keep separate. So it's the same thing with Rasmussen. Michael talked about splitting is going to be such a unique neighborhood expander. That, yeah?
This figure, so where do we see the unique neighborhood? There are also black edges going into that cell. So
Oh, this is not the cell. So, very good question. And again, yes, also everybody asks questions, please. So basically what you just did was I took my right-hand side, which was a set of all output position characters, and divided into the output position characters at position 0. Those at position 1. So here we have the whole alphabet, different characters in here, which are all at position 2. So this is not a single element here. So the other ones map over here. This one is only one that maps to this particular one. So we have, again, the full alphabet, different characters inside this slot. Okay, but I should have made that clear before. Okay. So why is this so relevant? So again, we get this unique neighborhood expander, and the point is, this is appealing that Michael and Rasmus have been using before, is that if we have a function that's k unique, so it's the same as P. And now if we have a random simple tabulation function that takes, again, b characters and map into some domain, then when we compose the two things, we get something that's k dependent. And it's very much the same argument as we had before. The point is, how does simple tabulation work, right? It takes, when we have the key x, first we get d different output characters. And then we look up all these output characters and get some random value. And then we XOR all these values. And the point is, x will now be the only guy who has this output character in the first round, and hence which uses a random value associated with that output character by the second simple tabulation function. So that means that the hash of x is independent of the hash of everybody else. And then the feeling says that it's k unique. It says that for any set of size of most k, you have a unique output position character. So now we can peel away x, and then by definition of it being k unique, it means that in the new set we can also find a key which has a unique character, which gets a unique random value. So now the hash of y is independent of what remains, and so forth. So the corollary is double tabulation, which first take my C keys and map into C characters and map into D characters, and then another simple tabulation function taking D characters into the domain of hash values. Then the composition is independent with some universal probability 1 minus little of 1 over y. Okay. And what do I mean by universal? The point is that I just need one k-unique function. And when first I have it, I can regard it as constant. I never need to change it again. So that's why I mean it's universal. This guy only has to be done once, whereas the second simple tabulation function has to be tossed each time we want something which is independent. Okay. So, as I said before, many of these things look pretty horrible, but it is also hard to get good constants in the closed forms, and many things contain loud and stuff like that. So I actually tried to do the calculations, and we say 32-bit numbers divided into 16-bit keys. I computed that I ended up with something 100 unique with probability 1 minus 1.5 to 10 minus 42. So this is really going to be 100 unique with very high probability in practice. So claiming that if you have a USB flash drive with random bits, that represents a universal k-unique simple tabulation function, that's going to be the safest part of the hardware. I mean, it's much more likely that you have other problems in your hardware than that. So in fact, you can just take your flash drive, fill it with random numbers, and say this is the magic function you always look for, and you are very, very safe. So the proof of this kind of thing is, I don't think I want to really talk about that. That's just, it gets a little bit subtle. You can look at these violations, which are a little bit like these trees the other guys have been talking about, and yeah, I will not really get into that. I'll just say that this Siegel's high-dependent hash functions have so far been a powerful theoretical, but far too slow for any practical application. And now we have this simple alternative, which is exponentially faster, and which also gives these fast unbalanced expanders. when I say something is independent, it means that when I say we have this level of independence, it means that for every single subset of the universe of this size, you have independence in that set. This statement is different. It says, you have one set in mind. I now get to toss the random coins, filling in the different tables. And now, on this particular set, or any set of polynomial number of these sets, I get full randomness in that set. But that still means that if you have an algorithm that runs on a limited number of elements, this number of elements, and that's the same as the space, so it's the best we could hope for. If it doesn't run on more elements than this, then with high probability, your algorithms are going to work exactly as if you have truly random hashing. There we go. Okay. So I'll just finish with, so I guess I'm finishing already as usual. Just my favorite open problem on, actually first, the Copenhagen had a question, which was just how do we fill in these different tables? And again, if you have questions, please ask them as we go along. So what I do personally is I go to something called random.org. They have this random bits that are based on atmospheric noise, and I download a megabyte, and then I have a megabyte of random bits, which is more than I would ever need. You could also, what you want is k-independence, then it actually suffices to just fill in your tables with k-independent data. So again, the proof that all these things work is just based on looking at k things at the time. So the tables themselves don't have to be truly random, they just have to be k-independent. Okay, so you can use your polynomial with these k different coefficients and use those to the pre-processing phase to fill in all the different tables, and then everything will work. But so, now the big question is sort of like, it would be a painful one depending on how it's answered in connection with this workshop, but the question is, really, do hash tables need hash tables? Right? Because everything we're talking about in this workshop is how great it is to have hashing because we can do hash tables. And one thing we should never forget asking ourselves is it possible to maintain a dynamic set of keys where you can insert and delete keys and ask if something is there in constant time? Worst case, deterministic. Right? So the trivial chain allows you to do everything in expected constant time. With the Google hashing, the query time is always constant because you just look at superposition. But the update time can easily end up being logarithmic because you have to follow these cycles around. So the question is really, do we need all this randomness? I mean, if we could, yeah. So again, we want to both insert and look up keys to constant and recent time. Deletions are easy if we do insertions. And so the best outer bound is square root of log n in the worst case. And that's actually type for a much more general problem, which is the predecessor problem. So the predecessor search problem, if you have a bunch of integers you have stored, when you do a search, you don't just say no if the thing is not there. You say what's the nearest key to what would be the predecessor if you had things stored. Okay? And for that problem, it's even a static lower bound, meaning that if you only use polynomial space, that's due to lower bound due to being effect. If you only use polynomial space to store your integers, then and you have unlimited time to figure out how to do your representation, you cannot do the searching better than this time. And strangely enough, deterministically we can't do better for the much easier problem. It appears much easier of just asking membership queries. It's much, much easier to do random if we use randomization. And so the two things are kind of related because the way we use hashing is just to shuffle the whole universe around randomly. And then we have done that. That sort of makes a search problem really easy because you just need to look at the first log n bits to basically find a key if everything is just random. And so it is really just searching